right, we are getting to wrap up this section 6.1 on sequences here. We've done a lot. It's a long section, I know. I'm feeling it. So we've done a lot of things. A lot of the sequences, first attempt would be just to take the limit as n goes to infinity. If it converges to a number, then that sequence converges. It's approaching a real number. If that limit goes to infinity, then the sequence diverges. If the limit doesn't exist, you may have to look more closely, maybe apply a squeeze theorem, maybe look at subsequences or something like that. Now, we ended last time with this notion of whether or not a sequence was non-increasing or non-decreasing, which is really just saying increasing and decreasing with equality allowed. And we said there's a few different ways that we can prove that. The first two just start with the definition and then either forming the difference or the quotient. The last one goes back to Calc 1. That's a way to show that a sequence is monotonic. Now, why would you really care about doing that? There's going to be other reasons later in the chapter, but we can combine that monotonic fact along with a bounded fact, and then we could conclude that a sequence converges. So, a sequence is bounded above if there is, pretty intuitive, a real number that is greater than or equal to all the terms in the sequence. It's bounded below if there's a real number that's less than or equal to all the terms in the sequence. And it's just generally called bounded if it's bounded above and below. So what we have here is a theorem that basically says if you combine monotonic and then kind of focus on which version it is with its corresponding bounded behavior, then we can conclude that it converges. So if you are non-decreasing, aka increasing, so increasing with equality, so let's just think about it as being increasing. So if I'm increasing and I'm bounded from above, then I know it converges. If I'm in reverse, decreasing with equality, so non-increasing, let's just say if I'm decreasing and I'm bounded below, then I can conclude that it converges. So that may come in handy for those situations where we can't just very easily evaluate the limit as n goes to infinity. So let's see what we can do with just some examples wrapping up, and we'll use those facts if we need to. So our first sequence here, 1 over 4n squared. So your first instinct should be to just look at the limit as n goes to infinity. So if I look at the limit as n goes to infinity of this sequence, 1 over 4n squared, that goes to 0. And so therefore, we would say that this sequence converges, and we found its limit. It converges to 0. Okay, that's the limit of the sequence. The sequence converges to 0. So a few ways we can say that. All right, now this next one is a little trickier. 2 to the n, well, that's geometric by itself. 2 to the n is a common ratio of 2. But then I'm dividing it by n factorial, and we did introduce that factorial here. So if you remember, if you were going to write out some of these terms to kind of get a feel for it, this would be 2 to the first over 1 factorial, so 2 over 1 would be 1. And then 2 to the second, so that would be 4 over 2 factorial, so 4 over 2 would be 2. If we did 2 cubed, that would be 8. 8 over 3 factorial, so 3 factorial is equal to 6. So 8 over 6 would reduce to what, 4/3? We did 2 to the 4th, we'd be at 16. So 16 over 4 factorial, that's 24. What does that reduce to? Dividing them both by 8, 2/3, right? Something like that. So maybe I'm kind of getting for a feel, it kind of looks like maybe with some of the first few terms, like maybe these are kind of, well, we have equality there and then decreasing, so maybe non-increasing. So as I kind of start to look at this, my gut is maybe telling me that we have a non-increasing situation potentially. So maybe that's kind of what we're thinking here. The issue is if I try to evaluate the limit. So if we were to say, well, why don't we just do what we've done in the other ones and just evaluate the limit as n goes to infinity, we're kind of stuck here. because the limit as n goes to infinity of 2 to the n over n factorial, I mean, this is going to infinity over infinity. Yeah, we could do L'Hopital's rule, but we don't know what the derivative, we don't have like a nice form of the derivative really for n factorial. So this one just doesn't work so well just trying to be evaluating the limit kind of from a strict analytical limit standpoint. So as we start to think about maybe looking at some of the things that we had up above, we start to list out some terms, maybe to get a gut instinct. Kind of feels like it's non-increasing. Let's see if we can show that. So let's take a look at if we have an nth term. So b to the n would be this 2 to the n over n factorial. So that would be our b to the n term. And then I would be comparing that with a b to the n plus 1 term. And so that would be 2 to the n plus 1 divided by n plus 1 factorial. When you deal with factorials, this is going to be a good time to, instead of forming the difference like we did last time, to form the quotient. So this is really where we are going to want to form the quotient. So let's just kind of think about, in essence, dividing by this 2 to the n over n factorial. So we're going to divide by the a sub n. So when you see factorials, that's a good time to do that. So on the left-hand side, we have 1. We're trying to make this comparison. Now, on the right-hand side here, dividing by a fraction, of course, we know is like multiplying by its reciprocal. So this is like multiplying by n factorial over 2 to the n. So you're going to deal a lot with situations like this as the chapter moves on. So let's kind of think about this here. So certainly if I have 2 to the n plus 1 in the numerator, and I have a 2 to the n in the denominator, dividing with the same base, you can subtract your exponents, and n plus 1 minus n is just going to be a factor of 2 in that numerator. Now, the factorials, once you do a couple of these, I promise they'll start to get easier. So we're going to represent the factorial kind of in an arbitrary general form. So the definition of a factorial is taking n times the integer below it, n minus 1, times the integer below that, n minus 2, and you take that all the way down until you get to 1. So if I was to expand out n factorial, that's what it looks like. Now, in a similar way, we can expand out n plus 1 factorial. We start at n plus 1, then we multiply by 1 less than that, which is n, and then we multiply by 1 less than that, which is n minus 1, and we take that all the way down to 1. And then guess what? What you really have here is n plus 1 times n factorial. So n plus 1 factorial is really going to be n plus 1 times n factorial. That will be a little fun fact that you'll just kind of start to observe as the chapter moves on. That n plus 1 factorial is n plus 1 times n factorial. So basically all of these factors, whatever they are, they all reduce. So what does that now leave you with on the right-hand side? So on the right-hand side, all you have remaining here is that 2 in the numerator over n plus 1 in the denominator. And you're trying to compare that with 1 for all values of n greater than or equal to 1. Okay, so if you sub in 1, you're going to get 2 over 2, which is 1. If you sub in 2, you're going to get 2 over 3. If you sub in 3, forgot where I was at, you're going to get 2 over 4, and so on. So this 2 over n plus 1, if for all values is going to be always less than or equal to 1, and that's going to be true for any n greater than or equal to 1. At 1, they're equal. After that, what's on the right is always going to be less than 1. So that's always going to be, that fraction is going to be less than or equal to 1. Okay, so we have definitely shown that this is non-increasing. So therefore, we are definitely, the sequence b sub n, in fact, let me put that in there. So let's actually say that here. So therefore, b sub n is non-increasing. So if we're non-increasing, so decreasing with equality, if we can also find a lower bound on this sequence, then we'll know it converges. So let's observe one other little fact here. So, and it's certainly true here. So let's think about this sequence. So this sequence b sub n equal to 2 to the n over n factorial for n's greater than or equal to 1. That is certainly never going to get to 0. In order to get to 0, you'd have to have a 0 in the numerator. 2 to any power is never going to go to 0. This can't ever be 0. This is always going to be greater than or equal to 0. So that means this is our lower bound. So we also found here that all-important lower bound on a non-increasing function. So if the function is non-increasing and it's bounded below, therefore we know that b sub n converges by that above theorem. All right, last one here, and I did kind of run into the space for the next one, but I don't think we're going to need that much space anyway for this last one. If we simply observe that a property of exponents says that a fraction or a quotient raised to a power, you can apply that power to both the numerator and the denominator. So guess what? This is equivalent to pi divided by 3. And so that means what we have is a situation that is a geometric sequence, and a geometric sequence, it's a weird looking cube, with that ratio that's the pi divided by 3, and that is certainly going to be greater than 1. And in those situations, that means that this sequence diverges. So if you remember those observations from last time, in order for a geometric sequence to converge, the common ratio needs its absolute value, if you had some negatives, would have to be less than or equal to 1. So this sequence diverges.